The paving process using the Wirtgen SP94 IDBI with high early concrete starts with the concrete truck unloading directly in front of the paver. The SP94I's 4-track sliding form system ensures stable movement as the machine moves along the designated path. As the concrete is fed into the hopper, it is evenly distributed over the form. The machine's intelligent electronic control system continuously adjusts parameters to maintain a consistent concrete flow and precise paving thickness. As the paving process progresses, the worker places steel dowels in the machine's steel dowel compartment. The integrated dowel inserter automatically places the steel dowels into the fresh concrete at regular intervals. This eliminates the need for pre-reinforcement and ensures proper load transfer between pavement slabs. A vibrator integrated into the form compacts the concrete, ensuring density and eliminating air pockets. The machine's modular design allows for smooth adaptation to varying paving widths, while the flexible steering system allows for maneuvering along curves or transitions. High early concrete setting allows for rapid hardening, reducing curing times. As the SP94I moves, it leaves behind a uniform, durable surface that is ready for immediate finishing and curing. The Wirtgen SP94I is a 4-track slipform paver designed for large-scale road and airport projects. With a paving width of 6 to 32 feet and thickness up to 18 inches, it features a modular design for flexibility and easy adaptation. Its intelligent steering and control system ensures precise concrete placement. An optional dowel bar inserter boosts efficiency by allowing direct dowel insertion during paving, streamlining the overall workflow. The Intel factory features the most sophisticated and automated manufacturing process in the world. It handles 12-inch wafers, transporting 25 at a time using the automated material handling system. This system precisely moves wafers between processing tools or to storage when needed, ensuring efficiency and safety. Real-time tracking ensures priority management. Without automation, modern production would halt, highlighting its critical role in enabling Intel's cutting-edge computing innovations. The JCB Teleskid begins the backfilling process by lowering the telescopic boom and tilting the bucket downwards. As it moves forward, the bucket makes contact with the soil and collects material efficiently, even below ground level, where a conventional wheel loader cannot. Once full, the operator retracts the boom slightly and raises it vertically to lift the load. The machine then reverses smoothly and rotates to the dumping area. Using the extended reach of the telescopic arm, the Teleskid easily dumps the bucket over the obstacle. The boom is then retracted, and the machine returns to the excavation area. The operator can raise the boom to place the bucket on a pre-positioned overhead steel bar to remove all the dirt from the bucket. Throughout the process, the operator benefits from improved visibility thanks to the single-arm power boom design and can safely enter or exit the cab via the side door. The precise grading process performed by a JCB Teleskid equipped with the David's Dozer V-lock blade. First, the operator lowers the V-lock blade to initiate rough grading. With smooth and controlled movements, the machine pushes soil across the site, spreading and leveling it evenly. The extended reach of the Teleskid allows the operator to grade areas around obstacles, such as pipes and manhole covers, without repositioning. Throughout the operation, the blade remains steady and responsive, adapting seamlessly to the surface changes. The operator uses both forward and reverse passes to refine the terrain, quickly cutting high spots and filling low areas. The system's high accuracy enables consistent control, with each pass improving the grade. Next, the operator performs finish grading. Subtle blade adjustments ensure that the soil surface reaches within 1/8 of an inch of the desired level. This precision eliminates the need for additional equipment or rework. The V-lock blade also shifts laterally and tilts to match site contours, maintaining a flawless finish even in complex spaces. In the final phase, the operator verifies grade uniformity by visually checking the smoothness and using the control system's feedback. The entire grading process is completed efficiently using only the JCB Teleskid and V-lock blade attachment. The D-Series bucket is a powerful and multifunctional attachment designed to maximize performance, safety, and efficiency in a variety of job site applications. One of its most innovative features is the telescoping front blade, which allows operators to doze, fine grade, and dig precision trenches without needing to switch tools. This flexibility improves job productivity and minimizes machine downtime. The blade also helps control material placement with exceptional accuracy, especially important when working in tight or sensitive areas. With its unique bucket design, the bucket allows users to grab objects across the full width of the bucket, making it ideal for moving large, bulky, or awkwardly shaped materials. Operators can also separate debris, contaminants, or excess materials efficiently, often without leaving the cab. This contributes to faster site cleanup and reduced physical strain, enhancing both safety and output. The bucket is engineered for safe operation next to buildings, walls, and other obstacles, thanks to its compact and precise functionality. Its design ensures excellent operator visibility, providing greater confidence and control even in challenging conditions such as downhill work or uneven terrain. This bucket excels in landscaping, construction, and general cleanup tasks. It can remove any size object, from small fragments to large obstructions, and reclaim excess material quickly to reduce waste. Its enhanced capacity and load control make it possible to handle heavier loads more securely and efficiently. In short, the D-Series bucket combines versatility, control, and durability, allowing operators to work smarter, not harder. Whether you're trenching, grading, clearing debris, or transporting materials, this attachment is built to handle the job with speed, precision, and safety, making site work faster and more effective than ever. The construction of Halabi at VGP Park Magdeburg reflects a modern, large-scale logistics and industrial development in eastern Germany. Located in the Star Park industrial area near the A14 motorway, this site offers strategic connectivity to key highways such as A9, A38, A143, and federal roads B6, B80, B91, and B100. The construction process began with extensive earthworks and site leveling, followed by the installation of underground infrastructure including drainage, power, and data lines. Afterward, a reinforced concrete foundation was laid, supporting prefabricated concrete columns and steel frames that formed the structural skeleton. Wall panels and roofing systems were installed next, ensuring weather resistance and insulation. Interior works included fitting custom administrative spaces, utility rooms, and technical systems tailored to tenant needs. Throughout construction, VGP emphasized energy efficiency and sustainability, adhering to modern building standards. The facility, comprising 86,043 square meters of rental space on 165,888 square meters of land, was delivered as a turnkey solution. With units starting from 3,000 square meters, Halley B accommodates logistics, light manufacturing, and commercial operations. Despite high demand, all available space is now fully leased, proving the site's value in the dynamic Halle-Leipzig metropolitan region. With its 1.7 million residents, the new JCB factory in San Antonio, Texas, marks a strategic expansion to manufacture large telescopic machines directly for the U.S. market. This move reduces overseas shipments from the UK, increases production capacity, and supports demand beyond the near-capacity Savannah plant. Gas Innovations reliably supplies high-purity refrigerants in bulk quantities to large-scale LNG terminals worldwide. With decades of experience, they provide key gases like propane, butane, isobutane, and ethylene. Their advanced logistics, dedicated transport systems, and strict quality control ensure safe, on-time delivery throughout all project phases. The trenchless installation of 110-inch concrete sewer pipes through pipe jacking is a sophisticated, highly engineered process designed to lay large pipelines with minimal surface disruption. This method is widely utilized in urban infrastructure projects, particularly in densely developed areas, under existing roadways, or within sensitive ecosystems where traditional open-cut excavation would be impractical or overly invasive. Unlike open trench methods, pipe jacking employs horizontal tunneling, using hydraulic jacks to push precast concrete pipes through the ground from a launch shaft to a receiving shaft, ensuring efficient installation with reduced environmental impact. The process begins with the excavation of a launch shaft, which serves as the starting point for the jacking operation. Excavation is carried out using conventional equipment such as backhoes or excavators, with the shaft's depth determined by the planned elevation of the sewer line and local soil conditions. To prevent collapse, the shaft walls are stabilized using steel sheet piles, concrete secant piles, or reinforced concrete rings, depending on the site's geotechnical characteristics. At the base of the shaft, a thrust block, constructed from reinforced concrete or steel, is installed to provide a stable foundation that absorbs the reactive forces generated by the hydraulic jacks during the jacking process. Once the shaft is stabilized and the thrust block is in place, a hydraulic lifting frame equipped with powerful cylinders is installed over the thrust block. This frame is aligned with extreme precision, using laser guidance systems and surveying equipment to ensure the sewer pipe follows the intended path. Even minor deviations in alignment can lead to costly repairs or structural issues, making accuracy critical at this stage. The first precast concrete pipe, often weighing several tons, is transported to the site via crane or heavy-duty winch. These massive pipes require careful handling, secured with ropes, slings, or lifting eyes. The pipe is lowered into the shaft, rotated to a horizontal position, and placed onto steel rollers or sled-like supports mounted on a hydraulic lift. These supports reduce friction and guide the pipe smoothly as it is pushed forward during jacking. Before jacking begins, the pipe's alignment is verified using a laser guidance system. A laser generator positioned behind the shaft projects a beam along the tunnel axis, targeting a plate mounted inside the pipe. This system allows the crew to detect and correct any horizontal or vertical deviations. Adjustments are made using pry bars, levers, or hydraulic mechanisms to reposition the pipe if the laser beam is not centered on the target. Precise alignment is essential, as small misalignments can amplify over long distances, potentially causing operational or structural problems. Next, the pipe joint is prepared for jacking. The spigot end of the pipe is cleaned to remove dirt, debris, or manufacturing residue and coated with a lubricant, such as bentonite-based slurry or synthetic grease, to reduce friction and ensure a watertight seal. The bell end of the previously installed pipe is inspected to confirm that rubber gaskets are properly installed. These gaskets are critical for maintaining water tightness, especially in high groundwater or pressurized soil environments. Hardwood reaction pads are placed between the new pipe section and the hydraulic jack plate to distribute the jacking force evenly and prevent stress concentrations that could cause cracking or spalling. Once prepared, the hydraulic jacks are activated, applying steady force to push the pipe into the ground. The lubricated spigot slides into the bell of the previous pipe, forming a secure joint. Throughout the jacking process, constant monitoring is essential. Workers observe pressure gauges to track the force exerted by the hydraulic system. A sudden spike in pressure could indicate an obstruction, misalignment, or hard soil conditions, which could compromise the pipe's integrity or delay installation. If abnormal readings are detected, operations are paused, the issue is assessed, and corrective actions are implemented to ensure equipment safety and pipe stability. After the pipe segment is fully jacked into place, the joint is inspected to confirm that the gasket is evenly compressed, the joint is tight, and the spigot and bell are flush. If the pipe includes lubrication ports or grouting tubes, bentonite or cement grout is injected into the annular space between the pipe's outer wall and the surrounding soil. This grouting secures the pipe, enhances soil-pipe contact, reduces settlement, and provides an additional barrier against groundwater infiltration. In high-pressure environments, an external mechanical seal or wrap, typically made of rubber or metal, may be installed around the joint for added leak protection. The process is repeated for each new pipe section: delivery, alignment, lubrication, jacking, and inspection. Laser alignment and pressure monitoring are conducted for every segment until the pipeline reaches the receiving shaft, which is excavated and stabilized similarly to the launch shaft. Upon completion, the jacking frame and support systems are dismantled, and the pipeline ends are sealed. The sewer line may then be connected to an existing network, fitted with manholes, or integrated into a treatment facility. Pipe jacking is an efficient, environmentally friendly method for installing large-diameter sewer lines. It minimizes surface disruption, reduces the need for road closures, and can be performed under buildings, rivers, or railways without damaging existing infrastructure. Advanced technologies, such as microtunnel boring machines, laser alignment tools, and sealing materials, ensure precise, durable installations. The Stickney Water Reclamation Plant, the largest wastewater treatment facility in the world, serves nearly 5 million people in the Chicago area. Using a combined sewer system, both stormwater and wastewater flow to the plant, where treatment begins with sedimentation in deep tanks. Heavier materials settle and are removed, while lighter particles move to aerated tanks. Here, microorganisms digest organic waste like shampoo and bleach, converting it into carbon dioxide and water. Final clarifiers separate remaining solids, leaving water that is 99.9% clean before being discharged into nearby waterways. The runway modernization project at Oradea Airport began with the first layer of asphalt mortar being poured on July 2nd and 3rd, 2015, covering the initial 500 meters of the runway. This marked the start of a broader effort to upgrade the airport's infrastructure to accommodate larger aircraft and improve operational safety. Starting on July 6th, demolition work focused on removing the remaining 1,450 meters of the old runway. This intensive phase continued through July 9th and July 15th, with heavy machinery systematically dismantling the deteriorated pavement and substructure. During this period, the worksite was organized to allow for efficient material transportation, safety management, and precise coordination among construction teams. As the old runway sections were removed, concrete pouring began on July 9th and 10th. This step involved laying a strong concrete base for the new runway surface, ensuring long-term durability and resistance to heavy loads and thermal stress. The concrete was poured using specialized equipment that ensured a consistent surface finish and accurate thickness. Simultaneously, on July 10th and July 15th, modernization work continued along the newly prepared sections, integrating the asphalt and concrete layers. These efforts included grading, compaction, and surface treatment to meet aviation standards. Throughout the project, site logistics were carefully managed to maintain progress and safety. The modernization of Oradea Airport's runway not only extended its operational capacity, but also significantly improved flight safety and service efficiency for future air traffic. The modernization process of the runway at Oradea Airport began on June 3, 2015, with extensive preparatory works. On this day, the construction team initiated the implementation of a new drainage system for the aircraft boarding and disembarking platform. This system was crucial for managing rainwater efficiently and preventing surface flooding. At the same time, work also started on the improvement of Taxiway Bravo, an essential access route connecting the runway to the main platform. On June 4th, a 350-meter portion of the main runway was targeted for structural upgrades. Excavation activities were conducted to prepare for the installation of the drainage system beneath the runway. Concurrently, a water drainage system was installed for Taxiway Bravo to ensure the long-term durability of the surface and safe operation during adverse weather conditions. By June 5th, a key component of the stormwater infrastructure was completed with the pouring of a concrete collection and discharge chamber. Renovation of the first 350 meters of the runway also progressed, including the removal of old pavement and preparation of the substructure. Compaction operations continued on taxiway Bravo, ensuring proper base layer consolidation before paving. On June 9th, the focus shifted to electrical and testing activities. Electrical cables for the runway lighting system were installed along the 350-meter section of the runway. In parallel, additional drainage components were laid. A significant step involved collecting laboratory samples to test the density and composition of the compacted materials. These tests were essential for confirming that the construction met required safety and engineering standards. Moreover, the main stormwater discharge chamber was constructed to support the new drainage infrastructure. This carefully phased and integrated modernization ensured that Oradea Airport's runway would meet modern aviation standards in terms of safety, durability, and functionality. The modernization process of Oradea Airport continued intensively through late July and early August 2015, focusing on expanding and upgrading the runway and its associated infrastructure. On July 22nd, work resumed on the main runway, with construction activities extending to the access roads of the decommissioned runway area. By July 24th, the installation of the rainwater drainage system along the runway had begun, alongside the construction of new access roads and preparations for a new boarding platform. Simultaneously, concrete pouring started on the takeoff and landing strip. This operation continued steadily through July 25th and into early August. The team also undertook the extension of the runway, ensuring it could accommodate larger aircraft and increased traffic volumes. On July 24th and 31, construction progressed on the Alpha Taxiway, an essential component for improved aircraft movement on the ground. By August 5th, large-scale concrete pouring operations were underway on the main runway, enhancing its strength and durability. The entire effort was carried out with precision and coordination to ensure the seamless integration of new and existing infrastructure. This phase of modernization represents a significant milestone in the airport's development, aiming to improve operational safety, increase capacity, and meet international aviation standards. The continuous progress reflects the commitment to transforming Oradea Airport into a modern hub for both domestic and international air traffic.